Hey, welcome to The Explainer. Today we're diving into something pretty cool. How do we actually teach a computer to, well, to see? How do we get it to go beyond just a simple grid of pixels and start to understand things like texture, shape, and form? We're going to look at some really powerful techniques that pull meaningful patterns out of images, giving computers a way more sophisticated view of the world.
Right. Let's just get straight to it. For a computer, this picture is nothing more than a big spreadsheet of numbers, each one just representing how bright a pixel is. So how on earth do you get from that, from raw data, to understanding a concept like, oh, that's a coarse texture, or I recognize that shape? Well, that's what this is all about, exploring the clever tricks that turn these numbers into rich, descriptive features a machine can actually understand and use.
So where do we even start? Well, our first step, let's call it level 1, is all about getting beyond that raw grid of numbers. And the simplest place to begin is with just a basic count, literally just looking at the overall spread up brightness levels across the whole image.
And the tool for that is called a first-order histogram. It's super simple. It just counts how many pixels there are for every single shade of gray. Now, this gives us a basic feel for the image, its overall contrast, but it has this one giant limitation. It totally ignores where any of those pixels actually are. It has no sense of space. To make that info a little more useful, we can boil the histogram down into a few key numbers. Variance, that tells us about the contrast. Skewness kind of tells us if the image is mostly dark or mostly light, and kurtosis describes how spiky that distribution of brightness is. It's a handy little statistical snapshot for sure, but it still tells us absolutely nothing about texture because it's missing that one key ingredient.
So yeah, here's the crucial point, right? Texture and shape, they're not just about what pixel values you have, it's all about how they're arranged next to each other. To get a handle on that, we've got to level up. We need to start looking at the relationships between the pixels.
And that brings us to level 2, describing texture. This is where we start actually seeing those relationships. The next tools we're going to look at do exactly that. They analyze how different pixel brightnesses are laid out next to each other so we can finally describe what we see as texture, with numbers.
Okay, so check this out. The Co-occurrence Matrix. This is a much more powerful idea. Instead of just counting single pixels, we're now counting pairs of pixels. We're asking questions like, how often does a really dark pixel show up right next to a really light one? This gives us a fantastic way to describe all those spatial patterns.
And this just perfectly shows the difference. From that matrix, we can pull out these descriptive features. Look at the coarse, blocky texture on the left. Notice that massive contrast value. Entropy, which is kind of like a measure of randomness, is also way up there. But then, look at the smooth texture. Both of those numbers are tiny. We are finally describing texture with actual numbers.
Now, the co-occurrence matrix is really powerful, but it can be, a bit of a heavy lift for a computer. So let's look at another absolutely fascinating and super efficient method for describing texture on a local level. It's called local binary patterns, or LBP.
The logic here is just so simple and elegant. You take any pixel, and you just look at its 8 neighbors. You go around them in a circle, and for each one you ask a simple question. Is this neighbor brighter than the center pixel? If the answer is yes, you write down a 1. If it's no, you write a 0. And at the end, you've got yourself an 8-bit binary number.
Stop and think about what just happened there. This one number, in this case 94, now represents the entire microtexture of that little 3x3 patch. It literally encodes the local pattern of light and dark spots into a single value. And if you do this across the entire image, you can build a histogram of these little texture codes to describe the whole thing.
Okay, so we've got texture down. Now it's time for level 3, capturing form. What about the overall shape or the outline of an object? Well, that requires a totally different approach, one that's all about describing the boundary of a shape. One of the classic ways to do this is with chain codes. Honestly, just think of it like a game of connect the dots for the computer. It traces the outline of a shape using a bunch of short little lines, and each direction, up, down, diagonal right, whatever, has its own number. So suddenly, a really complex outline gets turned into a simple string of digits like 0, 1, 1, 2, 3, and so on. But there's a catch. If you take that shape and you rotate it, or you make it bigger or smaller, that whole sequence of numbers, the chain code, it changes completely. We need something more robust, a tool that can recognize that a shape is the same thing, no matter its position, its size, or how it's turned. And this is where moment-based features come in and completely change the game.
It's kind of like how we summarized histograms before. These moments are a mathematical way to summarize the properties of a shape, and the real magic comes from a special set of these, known as Hughes invariant moments.
Okay, just look at this. It's incredible. On the left, we've got this Byzantine musical symbol. Now look at the table. Even when that symbol is shrunk, down, rotated, or even mirrored, the values of its hue moments stay almost exactly the same. That is the key. It's like a mathematical fingerprint for the shape. This is how a computer can reliably say, yep, that's the same object no matter how you show it.
So, let's bring it all home in our last section here, the toolbox for seeing. We've basically gone from a simple grid of numbers to building up this really powerful set of tools, and each one gives the computer a totally unique lens to see and interpret the world with.
So let's do a quick recap of our toolbox. We've got histograms for just a basic read on brightness and contrast. We have co-occurrence matrices for doing a really deep dive into texture. We've got LBP for a super fast, local snapshot of texture. We have chain codes to literally trace an object's outline. And finally, hue moments to capture the fundamental essence of a shape no matter what.
And all this leads us to a really big question for today. In the age of deep learning, where these giant AI models can just figure out features on their own, are these classic methods we just talked about, are they obsolete? Or could these transparent, human-designed, handcrafted features, where we explicitly tell the computer what to look for, actually be the key to building an AI that we can understand, and more importantly, that we can trust? It's something to think about. Thanks for tuning in.